Now let's explore orthogonal frequency division multiple access technique slightly in more detail. So there exists several multiple access techniques in the wireless ecosystem. You have TDMA, you have FDMA, CDMA, and OFDMA. So on this side of the slide, I am showing all the different multiple access techniques. So here you have, on this axis you have frequency, here you have time, and here is your transmission bandwidth. So you can, and say if you have 5 users, right? In a TDM system, you would allocate your entire frequency to every user, but you would have them use that frequency chunk on different time slots. So they would have the access to the entire frequency, but only for a given amount of time. So this is your TDMA multiple access technique. In a frequency, you would have 5 users, same as before, but now you can divide your entire frequency in chunks of 5, and you can allocate each chunk to each of the users, and that particular user would use that entire chunk of frequency for the entire duration of time. Now you can go into what is CDMA, where you can have them. Uh, so in CDMA, actually you have codes, and what you do is you share your entire frequency and you share your time of transmission with all users. The difference being you scramble the data for every user by a unique code that is specific to a user. And on the receiver side, the data can only be decoded if you had that specific code. So it's essentially a means of sharing your entire frequency and your entire frequency among all your users. So that's CDMA. In in OFDM, this is pretty smart. So what you do is you divide your frequency in small chunks. They don't have to be of all of the same size. And what you do is you allocate chunks of this spectrum in both the frequency domain and the time domain. So say, for example, here user A is using this frequency, but only for this time duration. User B is using this chunk of frequency for the same amount, for the same time duration as A, but there would be no interference because the frequency that's being used by B is different from A. And then you can also divide, you can obviously divide it in terms of time as well. So user D uses the same frequency that's used by A and B, but it only uses it when A and B are done using it. So this is the chunk of time that it's using, right? So you can have a more flexible allocation of resources in OFDM compared to the other access techniques, which is really important in LTE. So that's why OFDMA was chosen by 3GPP. So OFDMA is actually not new, and it has existed for quite some time. It's been there, but they've just leveraged it for LTE. Like I'd said, the idea is to divide entire bandwidth into chunks called subcarriers. These subcarriers then can be allocated in time and frequency domain. And because of some complex math, the subcarriers are actually orthogonal in nature so that they don't interfere with each other. And these subcarriers kind of look like this in time, in frequency domain, where, as you can see, the nulls of these subcarriers are on top of each other, so they don't interfere with each other, and they are separated by a given amount of time. And this picture here just illustrates that concept of OFDM and OFDMA. So in OFDM, you divide your chunk, right? You divide your entire frequency in chunks of spectrum, you allocate them to different users. In OFDMA, you take it one step further, where you assign your subcarriers in time and frequency domain. So it's a two-dimensional split, whereas OFDM just by itself is a one-dimensional split. This is another way of looking at it, where here you have time domain, you have frequency domain. Here you have these subcarriers that have their nulls overlapping so that they don't interfere with each other. These are called subcarriers, right? And this is, we are looking at a 5 megahertz bandwidth. And the way you go from frequency domain to time domain is by taking your fast Fourier transform, or FFT. LTE provides different modulation schemes depending on the needs. It offers the flexibility of QPSK, 16 QAM, 64 QAM. Actually, the newer releases also offer 256 QAM in the downlink. In uplink, we only support QPSK, 16 QAM, and 64 QAM. There is not support for 256 QAM in uplink as of yet. There is the concept of cyclic prefix in LTE. What that does is it actually takes a copy of part of the signal and appends it to either sides of the signal, so that it becomes more robust to intersymbol interference. And LTE defines two kinds of cyclic prefix, the normal and the extended. Depending on the channel conditions that you have, you can use one of these. And there is a set 15 kilohertz subcarrier spacing between each of these subcarriers, and that ensures that they don't overlap with each other and they don't interfere with each other. If you look at in LTE, the transmission actually happens every 1 millisecond. So if you were to look at RF coming out of a E node B, you would notice that once every millisecond, the E node B transmits data. And this interval is also called TTI, which is called transmit time interval. Now let's take a closer look at the building blocks of this TTI. So one TTI, like I'd said, is 1 millisecond, right? So that 1 millisecond is referred to as one subframe in LTE. One subframe is composed of two slots, slot 0 and slot 1 in one subframe. Each slot is equal to 0.5 milliseconds. So two slots make up 1 millisecond. 1 millisecond is one subframe, and one subframe is one TTI. One radio frame represents 10 milliseconds and has 10 subframes, because each subframe is 1 millisecond, and has 20 slots because each slot is 0.5 milliseconds. Now within each slot you can have a certain number of OFDM symbols, and in this case I'm showing 1, 2, 3, 4, 5, 6, 7. You can have 7 OFDM symbols in this instance. LTE does allow 6 OFDM symbols as well if you were to use extended cyclic prefix, but in a normal cyclic prefix you can get away with 7 OFDM symbols. Here's another way of looking at the same concept. Here you have frequency domain on this axis, you have time domain in this axis, you have your different subcarriers, right? Your subcarrier spacing is at 15 kilohertz. There is a concept of one resource block which refers to 12 subcarriers, which equates up to 180 kilohertz. And this resource block spreads obviously on the frequency domain. It encompasses 12 subcarriers, but on the time domain, it refers to as one slot. So one slot given is zero point 0.5 milliseconds. So this is a resource block. So one resource block is 12 subcarriers for a period of one slot, which is zero point 0.5 milliseconds. So same as what we had learned before, one subframe is equal to 1 millisecond equal to 1 TTI is equal to one resource block pair. So one resource block is actually composed of two physical resource blocks, where one physical resource block is 12 subcarriers spread over one slot. So one resource block is two physical resource blocks, so this guy and this guy. And you can have UEs sharing this time and frequency space. In this case, we have 6 UEs sharing, where each UE is allocated a chunk of spectrum for a given amount of time, and they can use within this chunk, they can use each of these any one of these modulation techniques, and the choice of the modulation techniques depends on the RF environment.